linear motion today. Linear motion is a topic that we covered back in, I don't know, unit 3 or 4. Particles moving around on horizontal axes, position function, velocity function, acceleration function, all that stuff. We've talked about this before. We're revisiting it today to talk about how integrals can be used in linear motion problems. The first time we did linear motion, we didn't know about integrals. We just knew about derivatives. Today we're going to use integrals. So there's a couple of formulas, or maybe 3 formulas, that I want to highlight right at the beginning. Most importantly, probably, is the following. Let's suppose that v of t is a velocity function. So v of t tells you the velocity of the object at time t. Then, the integral from a to b, v of t dt, is the displacement of the object from time a to time b. Okay? Now, why is that? Well, you might suspect that this is true just by thinking about the units of what this integral represents. I think we've mentioned this before. V of t might be measured in something like meters per second. Time itself might be measured in seconds. So the units of the integral would be meters per second times second, which is just meters. That's kind of a clue that this integral represents some kind of distance because its units of measurement would be meters. But why is it displacement and not, say, distance traveled? You might remember that there are 2 different kinds of distance in linear motion. There's displacement, which is just like final position minus initial position. And then there's distance traveled, which is like how many steps you walked, right? So if your journey begins and ends in the same place, like you wind up exactly where you started, then your displacement will be 0, but your distance traveled will be something else. So anyway, why does this integral give you the displacement and not the distance traveled? It's actually pretty easy to see why. Because if you wanted to compute this integral, so why? If you wanted to compute this integral, you'd have to find an antiderivative for v of t, wouldn't you? You'd have to find an antiderivative of v of t and then plug in b and a and subtract. Well, what's an antiderivative of the velocity function? The position function, right? The position function would be an antiderivative of the velocity function. So you could use the position function, which I usually call x of t, and evaluate that from b to a. So that would be x of b minus x of a. But look, that's what displacement is. X of b, that's your position at time b. X of a, that's your position at time a. So that's final position minus initial position. That's displacement. Okay? So if you integrate a velocity function from time a to time b, you're going to get the displacement of the object over that time. If you're interested in the distance traveled by the object, there's a couple of ways to think about it. Okay? The distance traveled is a little more complicated. So why is the distance traveled more complicated? Well, let's say that my velocity function looks like this, t times sine of t. Let me just graph that between 0 and 3 pi. So let's say that our velocity function looks like this, okay? Here's what's going on. Some of these regions are above the x-axis. Some of them are below the x-axis. If you integrate this function from 0 to 3 pi, the integral will treat some of these regions as positive, some of these regions as negative, and you'll get some cancellation. Essentially, the integral will treat this area here as a positive displacement. It's a positive area, so if you integrate from 0 to pi, if you think about the area under the curve here, that's going to be a positive displacement. In other words, it's a displacement to the right. But then if you integrate from pi to 2 pi, this region's below the x-axis, it's going to be a negative area. That's going to be a negative displacement. In other words, it's going to be a displacement to the left. And then this guy, of course, is going to be a positive displacement. If you just integrate this function from 0 to 3 pi all at once, the positive displacement here and this positive displacement here, some of that positive displacement to the right is going to get canceled by the negative displacement to the left right here. If you want distance traveled, that's not what you want. If you want distance traveled, you don't want displacements to the right and the left canceling each other out. You want all the displacements to be combined positively. Like you want to make all the displacements positive and add them together. You might remember that's the process for distance traveled. Make all the displacements positive, add them up. So, one way to find the distance traveled is to calculate each of these three regions separately. Do three different integrals. One integral for this region, you'll get a positive number. Second integral for this region, you'll get a negative number. Another integral for this region, you'll get a positive number. And then what you do is you make all of those areas positive and add them up. Okay? This function, by the way, we don't know how to integrate this, I don't think. I don't think we know an antiderivative for this guy, but I just made this up as an example. In the actual examples, you'll be able to integrate. So one way to do distance traveled instead of displacement is basically you've got to look at your graph. You've got to figure out when does it change sign, right? You've got to figure out when does it change sign. In the notes for today on the worksheet, I sort of do an example of this in more detail. At the beginning, the example starts here. I say, here's the velocity function. And first I say find the displacement, which is very easy. You just integrate from 0 to 3. But for distance traveled, it's more tricky. The velocity function looks like this. It dips below the x-axis. And so you're going to have to compute several different integrals. What you're going to have to do is you're going to have to figure out when the velocity function changes sign. And if you do a sign analysis of the velocity function by, setting it equal to 0 and solving, you'll see that it changes sign at 1 and at 2. So you would have to do three separate integrals. One integral from 0 to 1, another integral from 1 to 2, a third integral from 2 to 3. These are the three values that you get for this particular function. The distance traveled would be 5/6 plus this number made positive. In other words, 1/6 plus this number right here. That would be the distance traveled. So that's one way to do distance traveled. There's another way, but you can only do it if you have a calculator, okay? And you won't always have one. You won't have one on this test. So you need to know both ways. So one way to do distance traveled is to figure out when the velocity function's positive and negative and do separate integrals over each region. Different way of doing it is the following. If you just integrate from a to b the absolute value of the velocity function, that will give the distance traveled in a single integral. If you integrate the absolute value of the velocity function, that'll produce the distance traveled in a single integral. Why does that work? Well, look, the reason you need separate integrals in the first place is because some of these regions might be below the x-axis. You get cancellation, blah, blah, blah. But if you throw some absolute value bars on your velocity function, that just makes all of the regions positive, right? And then you can just integrate cleanly all the way from the beginning to the end, one integral, right? Compute all of it, and the whole thing will be positive, automatic, no need to break it up, blah, blah, blah. So that's super cool. But why do you need a calculator? Because we do not know the antiderivative of absolute value functions. Okay, we don't. In fact, they kind of don't really have an antiderivative. So if, you could say, oh, the distance traveled is going to be like, 0 to 3 of absolute value of whatever the velocity function is. I forget what it was, right? You could do that, but the problem is you're not going to be able to find an antiderivative of this function. because of the absolute value bars. They mess it up. We don't know an antiderivative for that function, so therefore this integral needs to be computed with a calculator or Desmos or something. Okay, so if you've got a calculator, if you've got Desmos, then distance traveled, you just do the integral of the absolute value. One integral. If you don't have a calculator, you need to be careful and do a sign analysis of the velocity function integrate over separate regions. So that's displacement and distance traveled. Last thing that I want to talk about today is average velocity. That's a concept that we've seen way back in the beginning of the year. You recall, the average velocity is just the average rate of change of position. So in other words, if x of t is your position function, then the average velocity will be given by just the average rate of change of the position function, which would be like x of b minus x of a over b minus a. And we saw that way back when. So why am I talking about this again? Because with integration, there actually is a second way of computing the average velocity, a new way to compute the average velocity. So this is the old way. We've known about this for a long time. If you have the position function x of t, you should just do this. There's not even any calculus involved in that formula, right? It's just plugging some numbers in and dividing. So if you have the position function, if you know x of t, use this. Same thing you've always done. But what if you don't have the position function? What if, instead, you only have the velocity function, v of t? Well, you might say, that's not a big deal, because if I know the velocity function, I could find the position function by taking the antiderivative, and then I could use this formula. That's true. That's true. Except, what if your velocity function is very complicated, and you can't find the antiderivative of that function? If v of t is very complicated, and you don't know its antiderivative, then you can't find x of t. You cannot find the position function, and therefore you cannot use this formula. There's a different way, though, of calculating the average velocity. So in this situation, where v of t is complicated, so you can't find the position function, instead, simply find the average value of the velocity function. The average value of the velocity function. Average value in the sense of yesterday's worksheet. We spent yesterday talking about average value. There's a formula, right? 1 over b minus a, integral from a to b, blah, blah, blah. There were some exercises on yesterday's homework which tried to get you to see this idea, that if you compute the average value of the velocity function, that gives you the average velocity, which of course it should. If you apply the average value formula to the velocity function, you would certainly hope that produces the average velocity. And it does. It does. In fact, the proof is not hard at all. Because look, if I take the average value over the interval a to b for the velocity function, what would the formula be for that? It would be 1 over b minus a times the integral from a to b v of t dt. That's average value applied to the velocity function. Okay, well, theoretically, if I found an antiderivative for v of t, I could evaluate this integral. Maybe in practice, this function's too complicated to anti-differentiate, but theoretically it could be done. And if I did find an antiderivative for the velocity function, it would be the position function, x of t. So this formula would be 1 over b minus a times the antiderivative, which would be the position function, evaluated from a to b. But of course, that's 1 over b minus a times x of b minus x of a, right? Just plugging in b and a into the position function and subtracting. But this thing right here, that's this. That's what this is. I mean, it's just a matter of putting this expression in the numerator of this fraction. You get the same thing. You get x of b minus x of a over b minus a, which is the average velocity. So this is a proof, actually, that the average value of the velocity function is the same thing as the average velocity that you've known about since the beginning of the course. So anyway, how does this help you? Well, as I said, so that's a proof that these two notions are the same. But I started talking about this to explain why this idea is useful when you can't find x of t, right? So how is this useful when you can't find x of t? Well, because you can use your calculator. Do you see what I'm saying? Like, if your velocity function is some crazy thing, square root of sine t, minus natural log of t, some kind of crazy function, and you have no idea what the antiderivative is, you can use your calculator to compute the average velocity. Average velocity from 0 to 3 would just be 1 over 3 minus 0 times the integral from 0 to 3 of this function. And if you have a calculator, then you can use your calculator to find the value of that integral, right? And then just divide by 3, and you've got the average velocity. And that allows you to find the average velocity even though you don't know what the position function is, okay? So the other big idea of this, in summary, there's really 3 ideas in this lesson. Number 1, if you integrate velocity, you get displacement. Number 2, if you want distance traveled, a little more complicated. If you don't have a calculator, then you need to see where the velocity is positive and negative and compute separate integrals. But if you do have a calculator, then you can just compute the integral of the absolute value of the velocity function. And then the third idea is average velocity can be computed in 2 ways. If you know the position function, just do the average rate of change of the position function. No calculus required. But if you can't find the position function because your velocity function is complicated like this, and you can't find the derivative, you can't find the antiderivative, you can still compute the average velocity if you have a calculator, because this integral can be computed using a calculator. The same thing, by the way, is true for like average acceleration. This comes up less often, but like it will come up in the worksheet. Just like average velocity, average acceleration, you can compute it in 2 ways. One way, which requires no calculus, is just the average rate of change of the velocity function, right? Acceleration is the rate of change of velocity, so average acceleration should be the average rate of change of velocity, and it is. So that would just be like v of b minus v of a over b minus a. So if you know the velocity function, average acceleration is easy to compute. Just do the AROC of the velocity function, no calculus required. But what if you don't know v of t? What if you only know the acceleration function? And again, if the acceleration function is simple, then you can anti-differentiate it and get the velocity function. Fine. But if the acceleration function is complicated, you're not going to be able to do that. And so what if A of t is very complicated? Well, you can still compute the average acceleration if you have a calculator. Because all you need to do is compute the average value of the acceleration function. That will be the average acceleration. In other words, it would be 1 over b minus a times the integral from a to b of the acceleration. That's the average value of a of t right there. That's what this guy is. And And even if A is very complicated, you can still compute this if you have a calculator. Okay, you're not going to be able to find an antiderivative, but you can still do it with the calculator. Okay. So really be aware of the fact that there are these two methods of computing the average velocity and stuff. The other thing is, throughout this worksheet that I'm looking at right here, we tend to give you very complicated functions. Like, look at this velocity function. That thing's a nightmare, okay? You're not going to be able to find an antiderivative for this. So if we ask you for the average velocity of this thing, like, you're going to have to use your calculator to compute an integral. You're not going to be able to find x of t, right? But you should be using your calculator throughout on this problem. Because it says in part B, for example, find the acceleration or let's even look at part B. So I mean, your first step is to obtain the same graph in your calculator. Punch this into your calculator, change your window so that it matches this window, like your y value is going from -2 to +2, and your x value is going from 0 to 5. Okay, try to get that on your screen. If it's not working, you can't figure it out, use Desmos. Okay, don't get hung up on the problem just because your calculator is being stupid. It says find the velocity at t equals 3.5. You know, you can do that on your calculator, right? Like, I mean, you could manually plug 3.5 into this whole thing, but once you've got this graph, you can just go to like second calc and then press value and type in 3.5. Acceleration at t equals 3.5, that would be the derivative of this function at 3.5. But we don't want you to find the derivative of this function. In fact, you don't even know how, because we haven't even talked about exponential functions. No, you can find this numerically using your calculator. It says use your calculator's dy dx function under calc. On Desmos, it's like, you know, it's stupid easy. You can just be like, you know, I mean, I know this is a different function, but look, like, if this is my function v of t, and I want to know the derivative of this guy at like 2, you can just type v prime of 2. And Desmos knows what that means. So like, you just define your function here and then type in v prime of 2. There's the derivative, right? So a big part of this worksheet is like using your calculator. You know, we give you these complicated functions on purpose to discourage you from like trying to find the derivative and antiderivative manually. We want you to use your calculator, okay? Yeah. So I think that's about it. Like I said, try to use your graphing calculator. If it's being stupid and not working, try Desmos, okay? All right, so I think that's it. That's kind of a long video. I will see you guys tomorrow.